Look at the public conversation around artificial intelligence, and you will find this same narrative. Tasks are being automated, and human labor is removed entirely. Evaluating these systems strictly through the lens of replacement creates a serious blind spot. It assumes the highest value of computation is to act as a cheaper substitute for a person, focusing only on what human labor can be stripped away. The actual architectural shift happening inside enterprise computing points in a different direction. It centers on a concept called intelligence amplification, or IA. Intelligence amplification is not a metaphor. It is an engineered socio-technical pattern, a tightly coupled system where humans define goals, constraints, and accountability, while computational networks contribute search, memory, simulation, and controlled action. It weaves computation directly into how people think and decide. The strategic objective here is not unchecked machine autonomy. It is the deliberate expansion of human cognitive capacity, using machines to handle routinizable work in support of insight and judgment. The theory of cognitive augmentation predates modern digital agents, with the core concepts appearing alongside the first programmable computers. In 1945, Vannevar Bush argued that science had multiplied our physical power, but left our mental power constrained. He called for new instruments that could give individuals command over the growing external body of human knowledge. By 1960, J.C.R. Licklider defined a logic of human-computer symbiosis. He proposed a division of labor where machines process structure and speed, leaving the human to focus entirely on hypothesis formation, criterion definition, and normative control. Douglas Engelbart then turned this philosophy into an operational research program. He designed new artifacts and interaction methods to explicitly improve the capability of people approaching complex, urgent problems. These pioneers possessed absolute conceptual clarity, but they lacked the necessary technical substrate: general-purpose networked computing, robust graphical interfaces, and the persistent working state required for durable cognitive delegation simply did not exist. Today, modern agent runtimes provide exactly that missing machinery. Because systems can now retrieve evidence, can maintain continuity, and produce inspectable traces, intelligence amplification has moved from a philosophical theory to a buildable engineering reality. To build this augmentation, we have to start with a baseline engineering assumption. A standalone large language model is inadequate for serious long-horizon cognitive work. A standalone model is epistemically shallow. It cannot anchor reasoning to verifiable evidence. It is operationally weak, unable to inspect environments or carry out bounded actions. And it suffers temporal fragility, losing all content resets without an external memory harness. An isolated language model cannot act as an agent. True cognitive capability requires embedding that model within a larger, externalized architecture. The solution is a 6-layer system that transforms a static predictor into a deep agent. At the core, the cognitive layer orchestrates goals and tasks. Above it, the tool layer integrates APIs and action primitives to manipulate actual software. Below, the memory state layer anchors the system, using explicit checkpoints and long-term artifacts to preserve coherence across extended workflows. Layering external tools and persistent memory changes the physics of the system. The model now functions as a continuous workflow coordinator. Granting memory and execution tools to an unguided system introduces severe risk. Amplification without explicit boundaries quickly becomes a loss of control. To regulate actions, we introduce the control layer. Human-in-the-loop middleware pauses tool calls requiring review, using programmatic interrupts as breaks for policy-bound access. Alongside it, the assurance layer provides visibility through trace-based evaluation, recording every decision and tool call into a structured audit ledger. Comprehensive logging and post-hoc review turn agentic cognition into an inspectable engineering discipline. You can benchmark, debug, and improve the workflow based on precise historical traces. Deploying highly capable agents without these specific oversight layers creates systems that are unsafe for consequential enterprise work. The objective is increased leverage, which means amplification only succeeds when machine capability is perfectly balanced with operational accountability. Sitting at the very top of this architecture is the final component, the principal layer. This is the human operator. Their exact role in this ecosystem is to provide intent, set strategic priorities, and define the absolute constraints of the task. While the machine executes the heavy analytical load, the human retains absolute accountability for the consequences and outcomes of the work. The tech industry routinely pursues fully independent, unsupervised artificial intelligence. That approach misinterprets where the real value lies in professional environments. The goal of an engineered cognitive system is not to remove the human from the loop. It is to elevate the human to the role of a strategic director over a highly competent, bounded tool. This complete 6-layer architecture represents our operational end state, the bounded cognitive delegate. This delegate carries significant analytical load, but it remains strictly tethered to factual state and evidence through its retrieval and tool layers. Crucially, when the system encounters high uncertainty, unmapped risks, or policy boundaries, it gracefully pauses execution and returns control to the human principle. This governed framework perfectly matches the actual risk profiles and deployment realities of modern enterprise environments, where accuracy and compliance are mandatory. True intelligence amplification requires building systems with deliberate boundaries. By establishing where the agent must stop, we ensure its capabilities scale safely. Deploying these Deepwork agents across a modern workforce fundamentally alters how an organization allocates its most expensive resource, human attention. Delegating routine synthesis, performing deep search, and complex tool execution changes the economics of expertise. Expert human time is freed from manual throughput. It moves upward, focusing entirely on problem framing, complex exception handling, and judgment under uncertainty. This dashboard illustrates the new metrics required to measure this shift. Traditional outputs per hour are replaced by measurements like decision latency, the time it takes to reach a well-reasoned conclusion, and evidence coverage, which tracks how thoroughly a system retrieved relevant data before acting. Measuring hand fidelity, the accuracy of context transferred between the machine and the human, alongside error detectability, provides a truer picture of productivity in an amplified organization. This modern operational reality matches the specific objectives identified by Licker and Engel, the augmentation of collective intelligence. Intelligence amplification is no longer a historical dream waiting for artificial general intelligence. It is the exact buildable architecture by which computation enters serious work today.